We have with here today Professor Artur Ekert, Professor of Quantum Physics at the Mathematical Institute, as well as Chian, Centennial Professor at the National University of Singapore, Director of the Center of Quantum Technologies. And I shall elaborate no further. Professor Ekert will be talking to us today about quantum cryptography, which I don't know much about, so shall not talk that much about it. Without further ado, Professor Ekert.
Oh, thank you very much. So very many thanks for this kind invitation to, well, let me just adjust this a little bit. Many thanks for this kind invitation to the society to come and talk to you tonight. As always, you know, when you asked to give a popular talk, it's very difficult for me to judge how should I pitch the level of this talk. So I have an idea what I want to tell you about, but if at any point you think that it's too simple or too complicated, just ask me questions, okay? So I want this talk to be more interactive than just me sort of presenting some ideas, etc. Anyway, so basically what I want to tell you about is the development in the art and science of secret communication. So we are talking about something that fascinated people for, you know, since time immemorial, basically. People were asking this basic question: what are the limits of security? Can we communicate with perfect security? Is there such a thing like a perfect cipher at all? So what I'm going to do, I'm going to give you a historical perspective first, so that you can see how things develop. Then I want to identify the major problem in cryptography today. And at the end of my talk, I'm going to tell you a little bit, you know, how quantum physics came into this and what we perceive as the limits of privacy today. It's not going to be very technical. There will be few equations, and but not much. Let's see whether I can handle this thing. Okay. So the outline of the talk is basically what you see here. I'm going to ask the question: is there such a thing like a perfect cipher? We'll talk about something that is known as the key distribution. I'll define the notion, explain what it is about, why people are so fascinated about it, and then I'll just say a few words how quantum physics entered this game. People thought for long that this is nothing to do with physics, that it's just about mathematics, it's about computer science perhaps these days, but physics was somewhat at the engineering level, but it isn't the case actually. It enters the subject at a very basic level. And then I will go a little bit more wacky and I'll start talking about the notions of reality and how this relates into the problems of security and what physicists have to say about this. And at the end, we go completely off the wall. We'll talk about scenarios which are the most exotic scenarios, where you assume that you don't trust anyone, you don't even trust yourself. Or maybe just a little bit, but not completely. So that's going to be, I hope I will just manage to and give you some kind of interesting perspective of this. During this talk, I would like you to have this simple scenario in mind. So I want you to consider two individuals, we call them Alice and Bob. And Alice and Bob are good guys. They want to communicate with each other. And there may be a third person, an eavesdropper, quite often called Eve, who may want to intercept this communication. So the question I'm going to ask is it possible for Alice and Bob to communicate in such a way that they are aware whenever there is an attempt of eavesdropping on each side? So they don't want to be fooled. They want to be confident that whenever there is any attempt to eavesdrop, they can figure this out. Of course, you know, this is a very simplified scenario for cryptographers. Today, cryptography is not only about this very simplistic scenario, but it's also about things like digital signature, password protection, authentications, and many other things. So I'm not going to talk about those things because that would take us a little bit off the main topic, and it would be, and also it's fair to say that quantum cryptography, which I'm going to talk later about, is basically about this kind of scenario. Bob in the past, when you go way back into the past, how Alice and Bob managed to communicate? The earliest attempts to communication in a secure way basically go into the Greeks. It's just about anything in Europe, right? So whenever you start any topic, you go to the ancient Greece or ancient Rome, and this is also the case with cryptography. When you have an alphabet, a set of finite symbols, it's relatively easy to mess them up in some kind of a systematic way. So as soon as we had alphabet, people started playing with the letters of the alphabet. And basically there are two operations that you can easily guess that you can perform. You can take any sentence and then you can permute characters, you can permute letters, you can permute symbols there, so that they are not in the same position anymore. And so those permutations were used by the ancient Greeks in a device that, in fact, they even came up with a device, it's a very simple device, I'll show it to you in a moment, called secrecy. That was about 400 BC. A little bit later, people came up with another obvious idea that instead of having a particular letter, you substitute one symbol for another. And that was called the substitution cipher. And allegedly, Julius Caesar used this cipher in about 50 BC. Actually, I'm not responsible for the spelling. It must be sort of like the cipher isn't quite spelled correctly. Never mind. And of course, you can combine permutations and substitutions and so on and so forth. So here's how Skittery looks like. So Skittery basically was the first device that people used to communicate secretly. And imagine two military commanders in ancient Greece, actually in Sparta. They would have a button of a certain diameter. And one guy would take a piece of parchment, would wrap it around the button, and write a message lengthwise. So you just write this message, and then you unwrap the parchment, and what you get is this thing here. You see that basically the letter A is still the letter A, but it could be in a different position of the parchment. So this was a device, a very simple device to implement the permutation of characters. But you give this parchment to a courier that will take it from one military commander to another. And the receiving guy would have a wooden button of the same diameter. So we'll just take the parchment, wrap it around, and the message will appear. So that was a very simple way of implementing. And so that was a very simple way of implementing permutation of characters. Substitution ciphers came a little bit later. And apparently Julius Caesar used a very simple cipher. It's about 50 BC, where he would use a substitution, which was determined by a very simple rule. What you do, you write the letters of the alphabet, and then you write another sequence of letters under this sequence, and you shift it by, in this case, by 3 characters to the left. And then you append those 3 characters at the end. So, so here then you have a very simple substitution rule, which basically says for A substitute D, for B substitute E, for C substitute F, and so on and so forth. And then the message that we saw before now is encrypted using substitution. So for A we write D, for T we write W, and for T again W, and so on and so forth. So this kind of ciphers are called monoalphabetic cipher because there's a clear one-to-one substitution rule. For each letter from the alphabet, you have another symbol, another letter, in this case determined by a simple shift of the whole alphabet by 3 characters to the left. Now, when you think about it, the number of possible substitution, if you have something like, I don't know, 26 characters, is actually quite huge. They don't have to be determined by the shift. Those substitutions could be just basically any permutations of characters. So you can write A, B, C, D, the original alphabet in alphabetical order. And then below, you can write any sequence, any permitted sequence, and that will determine substitution rule. So you know that there will be something like, well, 26 factorial of all those possible substitutions, which is roughly like something 10 to the 26, which is a huge number, 10 to the 17 in seconds is the age of the universe. So at the first glance you would say, gosh, this is a really fantastic thing. I mean, with this number of substitutions, it would be extremely difficult for anyone to figure out what this substitution is. So therefore, at a very superficial level, the cipher looks like pretty secure. But it isn't. And it was the first systematic method of breaking those ciphers was proposed by a person called Al-Kindi, who lived in the 9th century. And he was, in the 9th century, there was a golden period of Islamic science, and he lived in Baghdad, and is known as the philosophers of the Arabs. And he did all kinds of things, but among other things, he was interested in cryptography, and he came up with a method that would allow, in a very straightforward way, to crack monoalphabetic ciphers. So what he noticed was that there are certain characteristics of the letters in the alphabet which are not changed when you substitute one symbol, one letter with another symbol. So for example, the frequency of characters. You know that in any natural language, when you write in English, it's not just the use of random choice of letters. You don't just drop those letters, you form words and sentences. And there is a statistic to any natural language. The certain characters are much more common than others. So for example, in English, the most common letter is the letter E. So if you use a monoalphabetic cipher to encrypt a regular English text, then you look at the most frequent character in the cryptogram, and you say, well, this appears more frequently, so it must be the letter E. And so you can use the frequency chart, which you can see here. And this is for the English language, but it turns out that most Indo-European languages are actually pretty similar from this point of view. So you can look at the frequency of different characters. You can also look at frequency of different pairs of letters and on triplets and so on and so forth. So monoalphabetic ciphers are very easy to crack using this very simple statistical analysis. It really is no-brainer. Today, monoalphabetic ciphers considered not even as a cipher, such as simple changing of the alphabet, switching from one symbol to another. So no matter what kind of symbol you use for the letter E, as long as consistently use that one, then you can just simply figure out that that symbol is the letter E, and that's the way to crack the cipher. So it's pretty simple, but it took people a while. Well, at the time, as you could see, it took people a while, a few centuries to figure this out. But nonetheless, today we don't use any of those ciphers simply because they're too simple. So what people did, if monoalphabetic ciphers are not good enough, then people try to come up not with one-to-one substitution, but perhaps one-to-many. So that way people propose polyalphabetic ciphers. It's very difficult. Historians are not entirely in agreement who was the first one who came up with polyalphabetic ciphers. They probably were invented by different people at different periods of time in different countries. But certainly one person who not only came up with the idea, but also came up with a simple mechanical device to implement polyalphabetic encryption was this chap Battista Alberti, who most of you may know him as Italian architect, but he was also interested in cryptography. There was a period of time where that kind of the turmoil and plots and cloak and dagger policies, so people effectively use cryptography a lot. So Alberti came with the idea that instead of using one-to-one encryption, you can use one-to-many in the following sense, that you can, for example, use one monoalphabetic cipher for the first character, another monoalphabetic cipher for the second character, yet another for the third character, and then you can return and repeat the sequence. So for example, imagine that you shift, using the sort of like the Caesar method, you shift the alphabet by, say, you can use these sequences, for example. You can shift the alphabet for the first character by 7, for the second character by 14, and by 19 for the third character. And then you go again, 17, 7, 14, 19, as far as the shifts are concerned. And Alberti came up with a device, a mechanical device, which is called the Alberti disk, where you have two concentric disks, which you can rotate with respect to each other, and then you write the letters of the alphabet on the perimeter of the disk. And the relative orientation of the two disks would tell you something about the substitution rule. So you rotate the disk by 7 characters for the first letter, and you use substitution by 7 to encrypt, say, S, by 14 to encrypt E, by 19 to encrypt L. But then you use substitution by 7 again to encrypt the second L. So you see, unlike in monoalphabetic ciphers, where the same letter L would be encrypted by the same symbol, when you use polyalphabetic ciphers, the letter L appears encrypted here as the letter E, but then at this position it appears as encrypted. The encrypted version of it is represented by the letter X. So the statistical analysis in this case is much more complicated. It doesn't mean it's impossible. In fact, it took people a while, but Charles Babbage is credited with being the first to break polyalphabetic ciphers in systematic ways. So there are ways of doing it, where basically you have to focus on the length of this sequence. So in this case, we are using 3 different monoalphabetic ciphers, as long as you can figure out how many of them you are using, so then you can use the statistical analysis of Al-Kindi type. But the bottom line is a little bit more complicated. Well, from today's perspective, it's easy for me to say a little bit more complicated, but you see, when it was proposed, it was in the 15th century. And it was only in the 18th century, or even 19th century, where those ciphers were really tackled in a systematic way. So it took people a while to come up with a systematic method for breaking polyalphabetic ciphers. But the Alberti's disk had impact on cryptographic devices. When people started building more complicated contraptions and devices for encryption, they basically were using more complicated polyalphabetic ciphers. And with the help of electromagnetic devices, those ciphers became more and more complex. And Alberti disk became effectively a set of this. So you would have rotors that we would use in machines for encryption. So probably the most famous machine that you probably heard about was the Enigma machine, which was constructed by Artur Ekert. He was a Dutch guy in the early 20th century, and that was extensively used by the Germans during the World War II. But even that polyalphabetic cipher, I mean, the Enigma implemented an extremely complicated polyalphabetic cipher, so many people thought that it's kind of tough to break Enigma because the number of combinations and substitutions was really enormous. But nonetheless, the first one who managed to break Enigma was Marian Rejewski. He was a Polish mathematician who used a very simple group theory method to break Enigma, and in 1939 the Poles passed the secret to the British, who worked on the Polish algorithm for a while, and then Alan Turing improved it, and Enigma became a little bit more complicated. So, but you know, the bottom line is more complicated polyalphabetic cipher, and sooner or later someone comes along and finds a method to break it. So the question is there really a perfect cipher? So when we go from Skittily, 400 BC, to Alberti display Enigma, those were at the time ingenious ideas how to implement encryption, how to mess up messages so that only those who are supposed to read them can read them. But nonetheless, people sooner or later came up with systematic ways of breaking those ciphers. So whatever ingenuity, or no matter how much clever ideas went into designing crypto systems, sooner or later another clever person will just come up and show that it is possible to break it, or the method of breaking it. So then you may rightly ask me a question now. So is there such a thing like a perfect, as a perfect cipher? Can we really come up with a scheme where Alice and Bob can communicate secretly without Eve really knowing much about it? And of course, I wouldn't be giving this talk if the answer was just no. But so the answer is yes, there is such a thing like a perfect cipher, which will be immune to any statistical analysis. And those ciphers are known as one-time paths. Basically, what you do is you give Alice and Bob two random and identical sequences of bits. And so basically, Alice and Bob have to establish the sequence of bits somehow. And you call this random sequence of bits, which I sort of mark here with a red background here, is called the cryptographic key. Then Alice, who wants to send a message to Bob, takes a message, writes it in binary, and then will add message bit by bit. So the message is added to cryptogram bit by bit, so that one bit of the message is added to the corresponding bit of the cryptographic key to get one bit of the cryptogram. So the bitwise addition is like any other addition, except that you stay within 0 and 1, so 1 plus 1 in this language is equal to 0. And because of the randomness of the key, if it is really truly random, the addition will transfer this randomness to cryptogram. So the cryptogram is truly random without any signatures whatsoever. So if you look at the cryptogram and you don't know the key, you see cryptogram as a random sequence of zeros and ones. So then the cryptogram can be sent over to Alice, from Alice to Bob, over any unprotected channel. Remember, whoever looks at it would just see basically a random sequence of characters. No statistical analysis would reveal at this point a frequency of characters. But certainly you have here in binary, but when you add it to the key, it becomes the frequency of natural language are masked by the randomness of the key, so you get the cryptogram. Well, so it looks random to anyone but Bob, of course, who get the cryptogram, takes the key, adds the two together, and recovers the message. So it was shown by Claude Shannon, one of the founders of the information theory, who was also working on cryptography, that this method of encryption, if the key is as long as the message, is used only one, and it's truly random and secret, it's known only to Alice and Bob, then you cannot break this cipher. No matter how much computational power you have, it's pretty secure. So what's the problem with this? So can you think about the problem that Alice and Bob may have with this kind of scheme? Yes?
They have to transfer the key beforehand.
Exactly. So the big problem is the key distribution problem. Every single time they use the key is not good anymore. They have to throw it away. They should not recycle the key. And with this method, there's a need to generate lots of sequences of random numbers, not only locally, but you have to make sure that Alice and Bob have identical sequences of random meaningless numbers. And the key distribution problem is a big problem. So if Alice and Bob are in 2 different locations, it's very difficult to design a scheme where you can guarantee the security of such a key distribution. Once the key is established and you believe it's secret, then it's not a problem because they use any public unprotected channel to use this method. But to establish the key became a holy grail of cryptography. And that was known as the key distribution problem. And people tried to solve this problem because it was quite clear that the difficulty is in the key distributions. Once you can distribute the key, then you have a perfect cipher. You can use one-time path. And basically today we have 2 possible solutions to this problem of the key distribution. One is a beautiful piece of mathematics, which is known as the public key cryptosystems, which is basically what you use whenever you want to make a purchase on the internet. If you want to order a book on Amazon, you set in your credit card details, and the public key cryptosystems are used to encrypt the data so that so they kind of protect it this way. However, there is an issue, and with public key cryptosystems, at least the most popular one, like RSA, which is commonly used. And the problem is that we cannot really prove the security of those systems. Those systems are based on plausible, but unproven mathematical assumptions that certain mathematical operations are very difficult to do. And so the one RSA in particular is based on the fact that it's very difficult to factor large integers. By difficult, I mean that if I give you a number, say number 15, and I ask you to factor it, then you say, okay, 2 prime factors, 3 times 5. So that's easy. But if I keep on increasing the size of the number, it will be getting increasingly more difficult for you to figure out what the prime factors are. So for numbers that are hundreds of digits long, it will be taking more and more and more time. And if you plot a diagram, a graph, this difficulty measured by the time you need to give me the answer will go exponentially, basically. And that's what computer scientists regard as inefficient, simply because at some point you don't even have enough resources to compute. In contrast, multiplication is easy because if the number increases, okay, the time increases as well, but not in a drastic way. It will be at most polynomial increase in time. So it is because of this difficulty those ciphers are secure, but it's not clear whether, we don't have a proof that factoring will be difficult for classical computers forever. There may be, one of you or someone will come up with an efficient algorithm for factoring. We cannot prove that factoring is inherently difficult. And moreover, we know that with quantum technology, if you can build quantum computer, factoring will not be difficult. A quantum computer can solve factoring problem in polynomial time. So somehow, the security of public key cryptosystems is a little bit uncertain. Basically, it is as secure as the slowness of technology is. So you may say, well, those guys trying to build quantum computers here in Oxford or somewhere else, they still have a long way to go. So as long as they're slow in their progress, we are secure. But this is not a good notion of security. Maybe they're slow, but who knows? There may be a breakthrough here and there, and that may not be the case. So quantum cryptography is another solution, which I'm going to talk about. For those of you who are interested in how public key cryptosystems work, well, there's a mathematics involved, but the idea is actually pretty simple. So imagine, for the purpose of explanation, that you have, if I want you to communicate, to send me secret messages, then what I can do, I can prepare a safe box, a mechanical device, with 2 keys. And one key would be for locking the box, and the other key would be for unlocking the box. So basically, the key that locks the box is not good enough for unlocking the box. Now, one of them, the key that locks the box, is called the public key, and the key that unlocks the box is called the private key. Now imagine that I can distribute all those boxes that I produce to all of you with a public key, a locking key attached to it. And I keep the private key with me all the time. So what you can do, you can write a message to me, you can put it into the box, lock the box with a locking key. And at this point, you cannot even open this box because it's only unlocking key that I have, the private key can unlock the box. So if you made a sort of a mistake or you wrote something that you didn't want to write, it's too late. Basically, you have to take another box and write a message, another message to me. Once you lock, you cannot unlock it. You send this box to me, and I can unlock it with my private key. So you see, there's no need for key distribution here because the public key is really public, known to everyone, and it's used as a locking or encrypting key. For decryption, I have my private key, which I can use, and I don't share this key with anyone else, so it's my secret. So there's no need for key distribution here because we managed to somehow use two keys in a different way. But of course, the question is, which you may ask, surely, if you tell everyone how you construct the whole thing, which is, people know how I construct the box, then knowing the public key, which is a sequence of numbers, we should be able to figure out the private key. The private and public key are not completely unrelated. They are related through some mathematical formulae, of course. And indeed, you can do that. But doing that requires operations like factoring. So here's the difficulty. So this is basically the idea for public key cryptosystems. So now we are going to leave classical cryptography for a while, and I'm going to tell you how quantum physics is going to solve this problem. I'm not going to, don't worry, I'm not going to go into all details of quantum physics, but I want to give you a gist of the idea. So basically, on one hand, quantum technology, quantum computers will destroy public key cryptosystems if we have quantum computers. But at the same time, what quantum technology takes away, it also gives back because it gives us quantum cryptography. So there are basically two types of quantum cryptography. One is based on Heisenberg uncertainty principle. The other one is based on quantum entanglement. And I'm going to tell you about quantum entanglement not so much because it was my contribution to the field, but more because it turns out that with quantum entanglement-based cryptography actually can offer some very interesting scenarios that I'm going to talk about later on. So the whole story of how quantum entered the game can be traced probably to a very interesting paper by Albert Einstein, who was very much concerned with the whole notion how the quantum physics is set up. Einstein was very unhappy about inherent randomness. He thought that quantum physics was basically rather superficial, rather phenomenological. It was not really fundamental. So Einstein was worried about and was coming up with all kinds of paradoxes, saying, well, if you take quantum physics seriously the way it is, this inherent randomness, then there are even certain scenarios where you can deprive physical objects of their physical properties. That he would then question the notion of reality. There will be objects which will have properties that you cannot really attribute to them. I'll come to this in a moment. So for Einstein, that was nonsense, and then he said, well, you know, that shows that quantum physics is not quite yet what it should be. So let me come to this point that Einstein was trying to make. So that was about the notion of polarization, the notion of element of physical reality. How much time do I have to end?
Until 9:15. So
Right, so
no,
I'm not going to give you that long. So let me just explain briefly what Einstein had in mind. Well, actually, I don't know, of course, what Einstein had in mind, but what we understand today, or what Einstein was worried about. So when you take any objects that you can perceive, like this cup, this object has certain properties. It has white color, has such and such shape, and you attribute those properties to this object. So you can somehow perceive or measure those properties. You assume that they have objective reality, they have properties of this particular object. And so is the case with quantum particles, you may think. For example, take a photon, and a photon has one property that is called polarization. In fact, if you take a photon has not just one polarization, but you can attribute polarization to every single direction along which you are going to measure polarization. So a photon can have, you specify a direction, and a photon may have a polarization along this direction. And you can measure polarization of the individual photons. You can build a device, you send a photon to this device, you determine orientation of the device, and the device will tell you what is the value of polarization along this particular direction. And whenever you do such measurements, you can come up with two different values, which is usually plus or minus in some units, say of H bar or something. So okay, so if it is indeed, if we can measure something, obviously it does exist. So if we measure the photon has such and such polarization, so it has such and such polarization along given direction. The question then is, can we think about the cases where somehow that is difficult, where we cannot attribute a polarization to a photon? So it turns out that if you produce photons in pairs using a certain physical process, which creates what is called entangled photons. I use this buzzword, it's entangled, but basically you generate two photons, and one photon goes in one direction, the other photon goes in another direction. All this is happening in a certain crystal. You take a strong laser light, you shine on crystal, atoms in the crystal got excited, then they go to the ground state, and they emit two photons in two different directions. So it turns out that photons in such generated pairs may not have predetermined values of polarization. If you start thinking about this way, that those photons would have a certain value of polarization, then you have a problem, because they may not. And this is actually about 50 years, actually almost exactly 50 years ago, an Irishman, physicist, John Bell, came up with a very simple test which would enable you to tell whether you can attribute numerical values to certain observables or not. You know, Einstein was still speculating at a very philosophical level. It was John Bell who came along and said, actually, it's not philosophy, it's not a philosophical speculation. You can come up with a testable proposition in this case. You can set up probably an experiment that would actually verify whether those photons have polarizations, whether you can attribute numerical values to those polarizations or not. And so here's a rough idea of the Bell theorem in one slide. So this is as mathematical as I will get today. So imagine that there's a source that sends those particles all the time. One photon goes to Alice, another photon goes to Bob. And imagine that you choose two different polarizations on Alice's side and two different polarizations on Bob's side. So Alice is going to choose whether to measure polarization A1 or polarization A2. Choosing A1, she can get two values, plus or minus 1. Choosing A2, she also can get two values, plus or minus 1, but along direction A2. And the same for Bob. Bob can choose polarization B1 or B2. Now, suppose they all exist, right? So that no matter whether you measure A1 or A2, you assume that A1, A2, B1, and B2 have numerical values. You may not know them, but they do exist somehow. So you can think about A1, B1, A2, B2 as random variables that can attain those two different values, B plus 1 or minus 1. So in each single round of this experiment, you measure one of them. So Alice is going to choose randomly and independently from Bob, whether to measure A1 or A2. And the same for Bob. Bob is going to choose completely random. He's going to use his free will to choose B1 or B2 for each incoming photon. So then they repeat the whole thing many times, and you can define another random variable here, which is defined as S, by this very simple formula here. So now, if it is really the case that B1, B2, A1, and A2 have numerical values which are well defined, then you can see that this random variable will have numerical values that could be can be either plus or minus 2. And we can read it from this simple expression here. You can see that you have the sum of B1 plus B2 or the difference between the two. So one of them has to equal 0 because either B1 and B2 are identical or different. So when they're identical, this is 0, and when they're different, this is 0 because one is plus 1, the other one is minus 1. So the whole thing here, therefore, could be either plus 2 or minus 2. So if you have a random variable that takes only two different values, plus 2 and minus 2, then you want to know what is the average. You run many, many times and you look for the average value. So it will be between minus 2 and 2, right? So the average is always in between those two extremes. And that's basically it. That's the statement, which is known today as the Bell inequality. A very simple statement. You say if there are those numerical values attributed to polarization, then this S is between minus 2 and 2. That's it. Many people thought about it probably, and it's such a trivial mathematical statement that before John Bell, nobody thought seriously about writing it down. But of course he had a good reason, because it turns out that in quantum experiments, when you really do this experiment using those entangled photons, you get something that goes outside this range. So there are many beautiful experiments today, but probably the most convincing, the first most convincing experiment was that one by Alain Aspect in the in the early 80s, 1982, in an Institut d'Optique in Orsay, where indeed this value jumped outside to minus 2. You know, it's not, I should say that this derivation of the Bell inequality that I presented is not usually referred to as the Bell inequality, but CHSH inequality by two other guys who came up with a different formulation, but it has basically the same feel and the same taste as original Bell's inequality. So clearly, the experiment showed that this value is outside the range minus 2 and 2. So what does it mean? So that if you think that you can really attribute numerical values to polarization, that's not quite right. We have to just abandon this notion, and we have to think, well, those values somehow do not exist prior to the measurement. I know it's weird, and it may not even be a proper way of thinking about those things. But if you take a simplistic view, that is the conclusion, that somehow your assumption that those values exist is wrong. They do not. You cannot attribute what Einstein called element of reality to those photons, because if you were to be able to do that, then of course, you know, you would never violate those Bell inequalities. You would just stay in the range minus 2 and 2. By the way, if you have any questions at any point, so please ask. This was probably the most technical slide I had. Well, the previous one. Yes, please.
So you said the formula had B1 and B2 in it, but isn't only one of them being measured at any one time?
Yes. One of them is, but of course, you know, you assume that the other one does exist. So what you do, if you look at this formula, that's a good question actually. When you look at this particular formula, you can, if you look at the average value, you decompose the whole thing. So the average value of S will involve 4 different correlations between random variables A and B. And you can estimate those correlations in the run of experiments. So it's a statistical one. Of course, for each one, you will be choosing one particular observable. So it would be one value on L's side and one value on Bob's side. But running it many times and choosing different observables, you will be of different orientations of A1 and A2, and B1 and B2. You will be able to reconstruct all the statistics that you need to estimate this. So now you have to ask, well, what it has to do with key distribution? Well, you probably have an idea. So if it is indeed the case that the photons do not carry predetermined values of polarization on the transit from the source to those two devices. If it is indeed the case that the polarization is not there, so if you somehow want to, but then Alice and Bob, of course, perform the measurements, so finally they see the outcome of those measurements. So somehow the value didn't exist until the very last moment. So you cannot attribute any numerical value to this polarization. So if you use polarization to then generate a key, you can get correlated outcomes on Alice's and Bob's side. But if you also see the violation, if Alice and Bob see the violation of Bell inequalities, they know that the photons were not touched, they were not measured. They retain this purity in a way that there was no numerical value. And there was no numerical value, there was nothing to eavesdrop at. So that's roughly the idea, that somehow saying there's no element of reality involved, there's nothing to eavesdrop, because information somehow is not there until you just measure something. So testing for the violation of those inequalities, testing for eavesdropping, because any act of eavesdropping is effectively a measurement on the carrier of information. So that's roughly the idea of how to prove the security in those systems. So if we use entangled photons, the random variables somehow appear in two different locations. They are correlated in some way, and they can be used on one hand by Alice and Bob to test for the violation of Bell inequality, and if Alice and Bob see the violation of Bell inequality on some subset of the data, then they conclude that the data is genuine. They were somehow not measured, not touched, not eavesdropped. So they use the remaining subset to correlate the bits in such a way that they have identical data and they retrieve the cryptographic key. So that was, I think, first done by colleagues of mine here in Malvern. So when I came up with this idea, of course, I was very keen to see it implemented this way or another, but nobody wanted to do experiments, nobody actually believed, nobody cared about this thing at the time. And except two colleagues of mine, John Rarity and Paul Tapster. At the time, they used to work what used to be called Defense Research Agency in Malvern in Oxford, well, in Malvern. And then it became Defense Research and Evaluation Agency, then it was privatized and now is known as a Kinetic. But at the time, John and Paul were interested in fundamental physics, even though they were doing this a little bit on the side. You know, at the time, in this establishment, if you don't take a laser and if you don't point it at a tank, you're not doing a good research. So, but somehow John and Paul managed to persuade the management that it may be justified every now and then to entangle two photons and see whether it's good for anything. So they set up experiment, and you can see a kind of fake but source of entangled photons. The way it looked was like this, but you see, this is the pumping laser, and this is those are down-converted entangled photons. But the reason I'm saying is some cheating going on here, simply because you wouldn't see usually those down-converted beams because they are too weak. So John and Paul put two reference laser beams to show you the directions where the down and where the entangled photon will go. And they are sort of injected into optical fibers and going to different locations where they are measured. So the experiment was pretty good and pretty convincing. But today we have many experiments, and quantum cryptography today is almost a commercial proposition. There are lots of interesting projects going on all over the world. Some in the United States, some in Korea, Japan, China, or where you use cryptography to connect trusted nodes. So you have clusters of computers where you keep secure data, and you have many of those nodes with secure data, and you want to transfer information from one point to another, so quantum cryptography is good for you. So it's a growing business now. I'm not saying that quantum cryptography dominates, certainly not true, but it is certainly the case in all the last few years. We saw a genuine interest, especially in the government sector, in the development of quantum technologies for the purpose of secure communication. So that is actually, if I were to give this talk a few years ago, I would probably stop here, and that would be the end of the talk. In the last few years, there was another interesting development where people started looking at situations where not only you don't, so you see with entangled photons, you don't have to trust the source. The source of entangled photons can be placed anywhere. You don't have to protect it. But in my original version of quantum cryptography, you have to somehow trust your devices. Your device has to be something that you understand, you know how it works. It should be just a solid piece of hardware that you have on your desk and you understand how it works. And on top of that, I made the assumption that Alice and Bob make genuine random choices. So they have free will and they can choose randomly which polarization they're going to measure. It turns out that those assumptions are not quite necessary. Certainly, the most interesting development is that we don't have to trust devices. It turns out that as long as we get a certain type of statistics, we don't have to trust devices. And you know, I should have seen it. I didn't. So it's quite often, and someone else, sort of a few years later, someone else pointed that out. And it's kind of interesting because it shows that your ideas can be more clever than you are sometimes. You know, you come up with something and you think you understand it, and you don't see all possible ramification of those ideas. And some people later on come and say, well, have you thought about it? And I say, well, I didn't, but it turns out that sometimes you can improve things immensely. So I'm not going to go into technical details of the so-called device-independent cryptography here. I think I suggest that you may look at the semi-popular paper in Nature that I wrote with a colleague of mine outlining how it works. But the good thing is that we can minimize the assumptions about what is needed for secure communications. So it's interesting, we don't have to trust the source. We don't have to trust devices. We don't even have to trust ourselves, by which I mean we don't have to trust ourselves in the sense that we have a complete free will, or that we have a genuine random number generator that makes those choices for us between A1 and A2 or B1 and B2. It turns out that if we have quantum correlations, if we have public channel, and we have a little bit of free choice. So in other words, if we have a little bit of a free will, if we can have a little bit of randomness at our location, then it's good enough. It doesn't have to be perfect. We can be partially manipulated by someone else, and we still should be able to set up a secure communication system. And that is kind of explained in this review paper that I'm referring to. So for all of you, for those of you who are interested in technical details, I suggest you take a look at it. And so the question is, you know, in this quest for secrecy, there was a long trip, long journey. I was telling about split theory, about alberti disk, about enigma, old broken, public key, possibly not secure. Quantum crypto and device-independent cryptography, those new developments are quite exciting because they suddenly break this cycle where for where we sort of believe that for any good invention in cryptography, sooner or later comes a pretty good invention on the code breaker side. It seems that with quantum cryptography it's not the case. And we can establish secure devices which are secure not because someone is clever and comes up with a mathematical system, but secure because the laws of physics make it into a secure thing. So it's still mostly basic research, but if you ask me why is it that physicists somehow contributed to cryptography, which was viewed as a mathematical subject for such a long period of time, then the only sort of answer that I can give is a simple puzzle, which I like because it shows basically the basic idea. So the puzzle, I'll give you the answer, of course, is like this, that we have this guy here in front of two doors, and behind the doors there are two rooms, and in the rooms you have, in one room on the right, you have 3 electric switches initially in position off, and they are connected to 3 light bulbs in another room, which are in position off. So they switch off. You know that there's one-to-one correspondence between the switches and the light bulbs, and your task is to visit each room only once. And once you are in the room, you can do whatever you want with the switches and the light bulbs. But once you leave the room, you're not allowed to enter the same room again. So your task is to visit each room only once and figure out what is the one-to-one correspondence between the switches and the light bulbs. Now, if you think like a mathematician or someone who likes abstract thinking, then you may say it's impossible, that you can even prove that it's impossible. You say, well, all I can do is to go to the first room with the switches, but then there is a problem, because if I take and put one switch in position on, I go to another room, I see that one light bulb is on, but there's ambiguity about the other 2. And of course, the same if you put 2 switches in position on, there's the ambiguity about the 2 light bulbs which are on. So there is, no matter what kind of combination of switches you're going to use, there will always be a problem with trying to identify all those light bulbs. So you say, well, I can prove it's impossible. But give this problem to someone who's like experimental physicist or an engineer for that matter. The person say, well, easy. This is for real, right? So I go to the first room, put one switch in position on, go to the second switch, put it in position on for say 10 minutes or so, and switch it off. Then go to another room. You see the one light bulb is on, one light bulb is off but still warm because it was, it generated some heat, and the other one is off. So you can solve this problem if you take it as a real thing. If you think about it not in an abstract form, but as a real physical situation. So this is what happened with quantum technologies and quantum physics. Computation is a physical process, and when you discover something new, like you discover quantum phenomena, you can give those physical phenomena which are responsible for computation and communication different functionality. So this quantum effect is like heat dissipation. Taking this into account and utilizing it, you can achieve something that was not possible within the classical domain. So somehow physicists thinking in terms of real factual physical situation quite often can get a better insight. I'm not saying, this is not like to say that mathematicians are useless or something like this. It's just saying that sometimes it's good to have a different perspective on the same topic. And that in the case of quantum cryptography and quantum computing, which is another topic I'm not going to talk about here, gave us lots of new interesting insights. And the fact that cryptography can be now pushed to the limits, where we basically see we don't need that much for secure communication. Quantum correlations, a little bit of free will, and not being thoroughly stupid by letting others know what the secrets are. It's just modern enough. So thank you very much. And if you have any questions, please let me know. Yes, please.
So I'm familiar to networks. You willingly repeat
Yeah, for quantum entanglement, you can construct quantum repeaters, and indeed you will need them to distribute quantum entangled particles for longer distances. So usually you use direct optical channel with a basic technology that we have today. You can talk about, say, maybe 30, 50 kilometers. But if you use quantum repeaters, so you can have a situation where you have two sources of entangled photons, and then sending pairs of photons in that direction, but also into a repeater that would be a device that would take two incoming particles, will perform the measurement and broadcast the outcome of this measurement, which will make the other two particles entangled. So that's called entanglement swapping. So you have one pair of entangled particles, those two are entangled, and you have another one, those two are entangled. And then you bring those together, which makes those two entangled. So that you can do with entangled particles. By a sequence of entanglement swapping, actually building quantum repeaters is very much on the agenda and is a challenge. You need quantum memories because there are some issues, but those photons have to come always at the same time. And so on and so forth. So many technical issues, but basically the idea is there, and it's possible, it's binding. Yes, please.
You said that Alice and Bob had to choose which bits they looked at to check whether they were being eavesdropped on, and then they could use the rest of it as a key. What if the attacker knew which bits they were going to check for eavesdropping, and only eavesdropped on the other bits? Would that?
Well, that of course wouldn't work in this case. So they make those choices randomly. So that's first, this randomness is very important. There's sources of local randomness. So they made choices, random choices for A1 and A2, and also they choose randomly which subset is going to be used for testing eavesdropping and which one is going to be used and converted into the key. So when you do all this distribution, you use that public channel, so we can communicate and we say, well, okay, for the test of value inequalities, let's take data 1, 3, 42, and so on and so forth. And so one person generates a random sequence of locations where those data will be used for testing of value inequality. So that has to be done randomly.
So wait, do they have to both test at the same places?
Sorry?
Do they have to both test at the same places, or does only one person test?
No, so we assume that Alice and Bob are in two different locations. And we also assume that they can use what cryptographers call public communication channel, which is a channel where you can broadcast freely. Everyone can listen to it. But this is the channel where you can find difficult to suppress, in a sense that you cannot suppress all broadcasting and substitute your own broadcasting for it. So those are known as public channels, and assuming that you have access to this channel, Alice and Bob will communicate publicly about some outcomes to test for the value inequality. They will also communicate about measurements they use, but will of course not reveal what kind of values they got for the data where the key is going to be generated. So those things can be done, many of those things can be done over a public channel without compromising security. Yes?
Do you not have trust issues with the person generating the entangled pairs? Because theoretically they could generate a set of entangled photons such that you knew the values before transmitting them and make it look statistically correct.
Well, that's a beautiful thing about the scheme, that you cannot. So you see, you don't have to worry about the source of entangled photon, because somehow the violation of value inequalities makes you trust this source. So there's no way, and you can show it, that there's no way to produce entangled photons and have, or say, produce 3 or more pairs of photons. 2 of them you send to Alice and Bob, and you keep the rest, and you perform the measurements, which tells you something about the measurements that Alice and Bob made. If you were to do this, Alice and Bob will not see the violation of value inequality at all. So this is a good question, but so the answer to this is, the beautiful part of the scheme is you don't trust the source. You don't have to trust the source. the fact that you don't care where those entangled follow, as long as the statistics you get is of the kind that violates Bell inequality. You know that there's no entity that somehow knew about those values, but because they genuinely do not exist. I made this sort of a little bit simplistic, but you can come up with more sophisticated proofs using quantum physics, or not necessarily quantum physics, or some nature of correlations, which shows that this is actually not possible. It's even more than that. You don't have to trust devices that you use. So for example, you have enemy, but your enemy is technologically superior, and you actually can purchase your cryptographic devices that measure polarization and do all this choosing A1 and A2, or B1 and B2 for you. As long, well, actually that's not quite correct what I said. You can get the devices, but you have to make the choices. So there may be a knob that you put in two different positions called A1 and A2, and Bob is put into position B1 and B2. And it may well be that it's not doing anything. If it is not doing anything, we don't see the violation probably of the Bell inequality. But if those devices allow you somehow to see the violation of Bell inequalities, they are genuine. So somehow the process of testing for Bell inequality is also for testing for how genuine those devices are. You don't care about the provenance. It can be provided by your enemy. If they violate Bell inequality, they're good enough. They pass the test for being trusted, in a sense. So that's a beautiful thing. And then I said even further, even if you assume that the random choices you make, A1 and A2, are somewhat, the eavesdropper knows something about those choices. It's still okay as long as an eavesdropper doesn't have a complete knowledge. So it's beautiful that you can really remove those conditions. You don't have to trust you don't even have to trust yourself. You have to trust yourself a little bit.
When you say somewhat random, what do you mean?
Right, so, well, of course, now we can talk for another hour or so, but it is a very good question. So the notion of randomness, the popular notion of randomness you may have, is something that is, the binary string is random, zeros and ones have the same frequency and they're not mutually correlated. But somewhat deeper is, the notion of randomness is something that is truly unpredictable, so that there's no entity in the universe to somehow correlate itself and predict what kind of value will appear in a given experiment. So that makes this connection to cryptography. If there's no entity that can make prediction other than it's going to happen with probability half 0, probability half 1, so that's what we call random. So that means that there's no somehow predefined, there's no history to this event, or there's no way of making a statement or for any other entity to know what's going to happen. So that's how randomness I would like to define. Now, what is somewhat random is if there is a partial information about such an event on any third party something. So of course, in mathematics you define randomness in all kinds of ways. So it's just there are certain sources of randomness where you cannot certify that the bits are independent, for example, and you assume that there may be some intercorrelation between those bits, and so therefore it may imply that there are some programs that generated those bits and someone may control those programs. So there's much more to this definition, but basically think about it as predictability by some external parties.
Any more questions? All right, so I guess it's a go.
Oh, thank you very much.
Thank you, Professor Ekert, for coming. Thanks everyone for taking time off this late evening as for the talk. We will have refreshments served outside. It should be ready already. Next week we will be having a talk on ocean geology about what are the modern instruments used to study seabed. So do come along as well. once again, thank you everyone. Have a good evening.
Thanks.